Hello, everyone, and welcome. It's a great pleasure to see how many requests we have received for this event today, and to see that we have so many of you connected with us today. So I'm Pierre Lanari from the University of Bern in Switzerland, and I have the pleasure of guiding you through this event. So we are here today to talk about XMapTools and how the software can help you with data reduction of LA-ICP-MS data. So XMapTools is a map analysis software that has been around for more than 10 years, and it is efficient in data visualization, especially for chemical maps, compositional maps. It contains a lot of tools for classification, segmentation, and map calibration. XMapTools was developed to perform quantitative metrology, and now it can be used to do correlative compositional mapping between different instruments where you can put your maps together and do the data reduction within one program. It is also able to perform petrological calculations to estimate modal abundances, for example, to determine local bulk compositions in the area that you investigated. And more recently, we included some add-ons for thermodynamic modeling, and this is the add-on Bingo Antidote. So XMapTools is available as binary for macOS and Windows. The program is completely open source, and it's available on GitHub. So you can download XMapTools from our website, xmaptools.ch, or by browsing through our GitHub repositories. So we have developed XMapTools to be able to perform this quantitative metrology based on compositional maps. And the first target, or the first application that was really at the core of the software development, is the electron probe microanalysis, or EPMA. And I want to show you an example of what you can do with XMapTools with EPMA. So you can calculate these mineral maps where each color now in this map is showing you the distribution of a mineral. You can, from this dataset, estimate phase modes based on millions of pixels. If we focus on one given mineral, for example, plagioclase here in yellow, then you can display the composition of this plagioclase. Here I'm showing you the X-anortite, that is a molar fraction of anortite in plagioclase, which means that in blue, you can see a sodic plagioclase, albite, and in red, you can see a calcitic plagioclase that is anortite. And you see that there is a very high degree of complexity of the distribution of calcium and sodium in the plagioclase, depending on where we are located in the domain of the map. If now I focus on biotite, the brown pixels on this image, we can use a minor elements like titanium combining with X and G, calculate the temperature for the biotite, and this is what you see now, a temperature map for the biotite. And it means that your thermometer can be now applied completely in a microtextual context. So you see the distribution, or you see your results, and you can visualize the differences across a texture, a microtexture, or, for example, some effects by different grain sizes. But one of the goals that we have been trying to achieve in the past few years was to try to apply this quantitative metrology method using LA-ICP-MS data. And in order to do that, there are a few key components that you need to include. The first aspect is you need a robust and efficient strategy for generating intensity maps. From these intensity maps, you will be able to segment, to classify the different minerals or phases that you have in the map area. And then you need a multi-phase calibration method that is valid for major, minor, to trace element to be able to calibrate each mineral, each phase in your mapped area. We need an accurate calibration for chemically zoned phases. And this can be a challenge like the plagioclase I showed you before, where we have, in this example, large zoning at the scale of the map. So we don't have an element that is constant across plagioclase and that we can use as an internal element standard. And last, we need a flexible map processor software for large data set. And this is why we have worked on developing the version 4.3 of XMapTools that includes now all the tools that we are going to present today to apply this quantitative metrology based on compositional maps obtained by LA-ICP-MS. And to summarize what we're going to show you today, it will be three important aspects. The first is the map generation module that allows you to go from the data you recorded with your instrument to these intensity maps. The second aspect is to have a multi-mineral, multi-standard calibration that can tackle the most challenging cases, like the plagioclase I showed you before. And I'll show you how important it is to determine the limit of detection values for individual pixels and to filter your maps for this limit of detection. So let's start with the first part, that is the data conversion, how we go from this signal that has been recorded. Here you can see the time on the x-axis and the intensity on the y-axis, and we are looking at the total signal over a measurement time of about 14 hours. And how do we go from this signal here to an intensity map for each element? Here we recorded 38 elements in this experiment. And for example, here on the top left, you see an intensity map for the unknowns, so for the map for Syria. We can also generate other maps, for example, an intensity map for the standard GSD1G, that's the second map on the left, and a compositional map for the standard as well for Syria, for the same element. And you can use those three maps afterward in XMapTools to calibrate each phase individually. The map that you see on the right are the background intensity map that gives you the value of the background before each raster, for each line on the map. The second is the number of sweeps for background, and the third one is the number of sweeps for unknowns, and you can use those maps to calculate the limit of detection. All this step can be done in this converter module where you can import the data, and if you have a log file, you can use the log file to determine when was the laser on and when was the laser off. Then you can apply the background correction, interpolate your standards, do some quality check, and then you can generate the maps for the primary standard. And we will show you that you can use several primary standards. And then you can also interpolate your intensity maps for unknowns and all the additional maps that we need to calculate the limit of detection. So in order to show you the converter module, I would like to introduce you to Thorsten Markmann from the University of Bern. And Thorsten will tell us more about this new converter module. Please, Thorsten, the stage is yours.
Thank you very much, Pierre. So what I'm going to do now is to show you this converter module, which is handling the raw data we have from our laser ablation ICP-MS instrument, and how we load that inside XMapTools and convert the raw data to intensity maps. To do so, we start with the interface of XMapTools. This is the first default window, and up here in the data conversion section, we can use the laser ablation ICP-MS tool, the converter, and we click it to start the converter module. And the first thing you will have to do is to say and direct the software to the folder, to the directory where your raw data is located on your computer. So we click this button up here, load data files, and it will prompt you with a window looking like this here on Windows, asking you for two files. Since we are using an Agilent, which gives us a time transient signal in one file, we have to select this data file, which is here. It's simply a CSV delimited file, and we can select this file and open it. In the second reoccurring window, it will ask you a second file. And this is the laser log file, and this is coming from our GeoStar software we have been using on this SI laser. It gives us information about the on and off of the laser, of the sample, pattern names, but also on the time, which is very important if we want to match the laser log and to gather the information to lay it on top of the time transient signal from our mass spectrometer. So what I'm doing now is I'm opening this log file, And the converter module automatically detects all the on and offs of this log file and tries to match it as best as possible with the time transient signal we gathered from the mass spectrometer. With a little tool up here with the plus and with the intensity data we know from the experiment and from the data we loaded in, we can zoom in and we see that the red line here is just trying to be matched with the on and off of the signal where we've applied at the beginning the first sample, the GSD could be as a standard material here. So this means we are satisfied with the selection of the signal patterns on the raw data, but it can occur that there might be some of time shift, and you could correct this manually with the button down here. In my case, the match is perfect for me, and I say now to the software that I want to extract those integrations, so the samples and background intervals from the raw signal. This usually takes only 1 second, and what we are now able to do is, in the left window here, it created a drop-down, and we can investigate now all the background measurements individually of our measurements. And we see that the matching of the laser log to the raw data from the mass spec was successful because we are always selecting the background before the sample's measurement. The next step here is that we want to subtract the raw intensity counts with the background measurement of the signal. So this means we need a function, and this we can use with the drop-down menu here. We need to select a function that is representing our background measurements the best over the course of the measurement. It could be drift and sensitivity or so. And we could select, in this case, and we recommend this, the step function, which gives us all the background measurements before each signal. And we're representing this the best with the step function. And we can apply the step function now to subtract the background from the raw signal. The result from this is a new intensity data we have now being shown in the middle. And this is now the sum of all the elements we've been measuring. So for example, I could go in the drop-down menu here and I could investigate the background corrected intensity data of calcium. The good thing is also, and we are now in the step of selecting the primary standard, we can again, as before, investigate each measurement on the primary standard. And in this case, we are talking about the GSD1G glass. And we can investigate each measurement individually. And the red bar is now showing us the selection XMapTool and the converter module is automatically detecting as a representative for the primary standard signal. This range can also be adjusted with the sweep times and the numbers you see down here on the left. What we now have to do is we need also to use a function to describe the signal of our primary standard in course of the whole measurement. So for example, I can use a polynomial function to see how the standard signal evolved over time in our experiment. And I could say apply and want to save this primary standard information to our XMapTools project. The good thing here is you're not limited to only one primary standard. You can select several and try them out later for your calibration, which performs the best. So in my case, I want to select more than one primary standard. This means I go back to this menu by clicking yes, and I can add a spline function of the GSD1G class, for example, and we see that it performs slightly differently than before. I say apply. I can repeat this for a second reference material we have been measuring while our experiments, and this you can do with the drop-down menu here. And this is the NIST-612 class. I can do the same polynomial function, but now on the NIST-612 class, I apply it, I save it to the XMapTools project, and I repeat that for spline function as well. If I'm satisfied with all the selections, I say no, and I continue to the third step of the converter module, and this guides you directly to the secondary standard. What the secondary standard section is now doing is basically a quality check for yourself, how your measurement performed or how your measurement was executed, how good it is reproducing a calibration, for example, on the primary standard using GSD1G, on another sample. In this case, it is a known sample, the NISTIX 12 class. So we're doing this calibration of using GSD1G with an internal standard you see down here. And in this case, I will choose calcium because it is a very robust internal standard. And we can interrogate in the table here now the deviation in a delta value in percent of the reference value of the NISTIX 12 class with the calculated value from our measurement. And we see how much deviation is between those two values. So for example, if I scroll down, I can go to the trace elements I measured, and we see that we are mostly within 5% or a difference to the reported preferred value for the NISTIX 12 class. This whole table you can also select and copy it to Excel, and you save your quality check, because after this step, it is not anymore feasible to do. So this is a very important part to check the quality of your data. If I'm satisfied with all those checks, I can continue. After secondary standard, I say apply. And now we're in the section where we generate the main map. So the map we actually acquired on our sample. In our case, it was a garnet sample with plagioclase, and as similar as before, we can see the intensity signal now background corrected for calcium over the whole turn of the map for one line scan in this case. And of course, we have some inhomogeneities, and this is why the intensity signal is varying much more. In this case, there's nothing else to do rather than selecting maybe a different sample, but I want to select the garnet sample, and I say apply. And this will now take a few seconds. What the converter module is now doing in the background, it is running the pixel allocation algorithm we have been coding and which we have published at the beginning of the year to extract the information from all those intensity data and is reallocating it to the pixels to create the maps of intensity. But it's doing this automatically for all the elements we have been measuring. This means for 38 elements from major to trace elements in this case. What it is also doing, it is saving all the information we want to have from the primary standard for each element. And since we have been saving 4 different primary standards with 38 elements, this can take a minute or so. So now in a few seconds, this should be done. And we would be ready to investigate the first results we got from the pixel allocation algorithm. So what I can do here, since it's finished, I can select now an element I would be interested in. So I could, for example, select vanadium. And then we're clicking this show button, and it will prompt us with a new window. Give me 1 second and I will expand it and you see it better. It will give us a window similar to the one Pierre was showing us earlier, which is a summary of your first results. It is the intensity map of vanadium, background corrected. It is the background intensity map for all the measurements. It's the number of sweeps on the background, so how many integrations on the background measurement we use to determine this intensity map. But it's also giving you the intensity map of the polynomial function of the GSD1G as an example in this case, which is now again showing us this polynomial trend we have been seeing earlier on the raw data. And it also gives us the information about the expected composition of your primary standard and the number of sweeps, around 3 in this case, which have been integrated for each pixel we see on the map up here. If you're satisfied with the result and everything looks fine, we simply have to say export. It is saving all the intensity maps we have been generating to text files in the background. So if I'm opening my folder, you can see that it will add step by step the text files to a folder, and you can open this by any other software or your own code to investigate it. But it also gives us the chance to later import those text files to XMapTools. It additionally also saves the primary standards. Since the converter module is finished, it will return back to the main window of XMapTools. And when we are here, we simply say in the import maps and images part that we want to import intensity maps. And this will ask you then for the directory of all the intensity maps, which will be in maps counts per seconds, which will be automatically generated in your project directory. And we can select all those intensity maps as text files, and we import them to XMapTools. It will then show you a window where it says that it identifies the intensity map of the element with this mass that has been measured on as intensity data, and we say simply import the data to XMapTools to then visualize the ready and allocated intensity map. For example, let's get me back to vanadium, as we saw before, to your XMapTools project. With this, the converter module is finished, and it goes back to you, Pierre.
Thank you very much, Thorsten, for this nice tutorial. I noticed that you have used data recorded in a single file and with the help of a log file. And another strategy that is also quite used is to use multiple files, one for each measurement. And to tell us more about that, I'm inviting Renée Tamblyn from the University of Bern to join us. Renée, please tell us more about the current compatibility of XMapTools regarding the input files.
Excellent. Thank you, Pierre. So as Pierre mentioned, another strategy for when you analyze a map by laser ablation, mass spectrometry, is that you end up with a different file for each scan that you've produced, including your standards. So when you export your data from the mass spectrometer, you often have something like this, where you have individual files. And as Pierre also mentioned, sometimes you will not produce this log file that Thorsten used just previously to process his data. So the next version of XMapTools actually has a way of dealing with that, which kind of opens up XMapTools to other labs and other ways of collecting this data. So again, we go back to this converter module that Thorsten showed us by pressing this button up here in the data conversion tab. And you will have just seen this window from Thorsten where he input just the single file, and now we'll do. So up here, you can see that we have the mass spectrometer information. Here we're importing from Agilent. Right now, that is the only option. But if you're interested in importing data from a different mass spectrometer, Pierre is very open to making that work for you. So please send your data through, and we can make XMapTools even more flexible for that. So now we're going to change from single file to multiple file, because we have multiple of these CSV files. And in this example, we don't have a laser log file. So this means we don't know when the laser was turning on and when the laser was turning off. So we'll load those data files that I just showed you before, which is from this folder. And a small trick, because this XMapTools is working from MATLAB, is to highlight from the bottom up the files you're importing at this stage. This just helps the files to import correctly into XMapTools. And it will read those data files in. And then in a moment, it will bring us to a screen which is quite different from what Thorsten just showed us, which is the log generator. And the log generator is going to basically make a file that tells XMapTools about when the laser was turning on and off, and things about the size of your map and the settings that you mapped at. We follow from the top left of this section. So first of all, we have the starting position of the map, the X and Y. In this case, we'll just leave them as 1. But these are 2 really important parameters which you need to import yourself. And that is the laser diameter, so the size, of your spot you used and also the scan speed. So in the example I will show you, the laser diameter was 10 microns, and we scanned at 10 microns per second. And this is really important because this is going to dictate the size of the map you produce, and the exact ratio of the X and Y axes of this map. So if you have this correct, then when you export your map from XMapTools, then it should be in the correct scale. This is important. This is also important if depending on what you're mapping, the scan speed can be quite important, as is discussed in Thorsten's paper. Of course, a slower scanning speed will get you basically a better count, better signal intensity when we interpolate in XMapTools. Regardless, so we have this important information in, and the next thing we'll notice is that here are all the files I loaded, and they have a file name, which is the number, basically the order these files were measured in, and the type. The first thing we want to do is to change the file name so that basically all of our map has the same file name and all of our standards have the same file name. And this is important for XMapTools to read. So this little unit up here lets you do that. So usually we have a delimiter between, either you have the name of your analysis followed by the number, or sometimes you have the number first. And the position, this name position, corresponds to if the name is before or after your delimiter, which you can also change. In this situation, our position is 2. The name of our file is after the number. And if I now press this button, apply to all, it will slowly, you can see it go through and edit all the names, making sure that all the standards, in this case, the GL3 and the map names are the same. Great. The next thing to do in this situation is you'll notice that all of these have been labeled as a scan type. In this particular scenario, actually, only the map was a scan and the standard was a spot. But we can press here and get a simple drop-down menu where we change it to spot. And the neat thing is once you do this for one, XMapTools will ask you, do you want to apply this to all the measurements with identical names? And this is the benefit of naming all of our standard files the same name. So now I can say, yes, all of our standards were spots, and it will change all of them in the list. So now that XMapTools knows about what standards or what our map is, spot scans, these sorts of things, we go to the really important part where we have to say our signal definition. So what is our background and what is our measurement? Essentially, what is our laser on and what is our laser off? And that is done down here. So if we, for instance, first select one of our standard spots, you can see here's our time integrated analysis for that single file. So here's intensity. This is the total intensity versus time. And first we'd like to select our background. So this basically is done by selecting sweeps, a cycle of the mass spectrometer measurement. If you're not really sure exactly what your sweeps were, that's fine, because you can add this region of interest button. This will allow you to measure basically the width of this time. So now we can see down here in this window that our sweep start and sweep end have updated with numbers. And these numbers correspond to the width of this box. This type of this analysis is a background. So we can select here, we have different options like background and measurement. In this case, I've chosen the background before the measurement, and we can add this to the table. And that will add now in the table, the sweep start, sweep end, and the type of analysis. So I'll reset that. Now what we want to do is we want to select the actual measurement itself, tell XMapTools what is the measurement, and we can see that here. Yeah, so let's call that our entire signal selection. And you can see down here, the sweep start and sweep end have updated. And this is the measurement, so I will select measurement and add this to the table. So these conditions only correspond to our spot analyses, which is our standard. So what I will do now is I will apply it, and we have some options here. You can apply to everything, apply to just the one analysis we're looking at, or apply to the same name. And I will apply to the same name because I want these same settings for my standards. And you can see here that is updated on the left-hand side. Now the next thing would be to look at our map, actually look at our scans. So if I select the first scan analyses, again, here you can see the background and the signal. The signal, as Thorsten pointed out, is much more variable because we're actually measuring across a map here. I will probably use the same background because I know in this the background is the same. However, if you have a different background, you can again update in this table by double-clicking and typing in sweeps, but I'll keep it the same. However, our measurement is much longer because we've scanned across quite a long distance. So I will add an ROI to see how many sweeps I need across my entire map. So there we have down here is updated. So the sweep start is 97, so around the same as our spot analyses, and the sweep end is 314. I could have also used this value here. You can see it tells you how many sweeps this entire file has. But in some cases, you might find that your mass spectrometer keeps measuring, but your laser has stopped ablating. So you actually have a drop off here in signal, and we don't want to include that in the map. So that's where the ROI can also be useful. So now what I will do is for the measurement in this table, I will simply update it to 314. And then the nice thing is I can simply apply this to the same name, and it will apply it to all of my scans from my map. If you have secondary standards or if you have several maps, this is also the way you can do it. So you can actually load in multiple maps that you've done over one session, and you will need to apply different settings for the maps, especially if they're different lengths or the scans are longer or shorter. So once we've done that, now we have this nice big button at the top, which says generate the log. And this will generate all that information into a log file that XMapTools can use. And this might take a little bit of time as it saves the data and saves the log file. And now we will be back at the same screen you saw Thorsten at. So this is the exact same screen as you saw before. We had one single CSV file. Now all of our files have been combined into one session. And you can check to see how well this has worked by zooming in. And you'll be able to see that these red lines correspond to laser on and laser off. And once that's been done, you can go through the exact same process that Thorsten showed before and have a look. And an important step here is at the end is to have a look at your map when you get this first ability to visualize it, and just make sure that you've got that scan speed and spot size right and that your map is in the correct ratio. Otherwise, I think that's all from me, and I'll pass it back to Pierre.
Okay, thank you very much, Renée, and also Thorsten for showing us this converter module. If I sum up what you have shown is that we have a slightly improved data compatibility compared to the previous version of XMapTools, where we added this log file generator and that you can try with your own data. This is still work in progress. As Renée said, I'm very looking forward for receiving a new type of data and make sure that they will be compatible with the next version of XMapTools. We showed you that you can easily get multi-standard interpolation with different interpolation functions. You have a nice quality checking tool in the converter module to tell you how good or bad was the session. And then you can generate those intensity maps for standards and unknown. And that's how we generate the maps that we're going to use in the next step for the map calibration. Let's talk a bit about this map calibration, because this is a very important aspect. And if we look at an area that we analyze, and this is an example of the map that Thorsten showed you, and this is an optical image of the area that we analyzed, where you see mainly 3 different minerals. We have this amphibole, plagioclase, and garnet. And it's a metagabbro, and it's a very nice corona texture. And I want to use that example to show you how important the multi-phase calibration is and how important it is to include the limit of detection calculation in the calibration. So first, what Thorsten did is to generate an intensity map for vanadium. And if we replace here this optical image by the intensity map of vanadium that Thorsten generated, now we are looking at counts per second. And you see that we have different intensity between amphibole in red, garnet in orange, and plagioclase in yellow and blue. And so the goal is to use this intensity map and to calibrate amphibole, garnet, and plagioclase separately with different calibrations, and to be able to obtain a fully quantified compositional map. And if we do that for this sample, what you obtain is this vanadium map that is now expressed in microgram per gram, and each calibration of each individual phase has been done separately. XMapTools also generate the map of limit of detection calculation. And here you see this map where you see for each different pixel, the limit of detection of the individual pixel measurement. And so it's expressed in microgram per gram in this case for vanadium. And you see that it ranges between 0.2 microgram per gram in amphibole to about 0.6 microgram per gram in our plagioclase. But what is key now is if we decide to filter every pixels in the map in the center that are below limit of detection, what we realize is that most of the plagioclase pixels are actually below the limit of detection. And so it is very important when you use maps not to use those pixels as represented a real measurement of the amount of vanadium that you would have in your plagioclase in this case. And this is why it is really important to do the multi-phase calibration and to be able to filter for the limit of detection. So this calibration can be done using our calibration module that we're going to show you in a minute, where you calibrate your intensities to microgram per gram. You can also, in the module, enter your reference data for your internal element standard, and we have some converter tools. For example, if you enter your composition in oxide weight percent, it will automatically convert it to element weight percent or element microgram per gram. You have also some ROI tools for assigning composition, you will see, for this variable composition calibration. And then there will be the generation of the calibrated maps for each phase using multiple primary standards. You can see on this image on the right that for each element, there is a different primary standard that can be selected. And we're going to show you this. And also you can use the fixed or the variable internal standard composition, and the module will produce those limit of detection maps. But to tell us more about the calibration module, I'm inviting Thorsten again, and he will continue on his project. Please, Thorsten, the stage is fully yours.
Thank you again, Pierre. What I'm trying to do, I follow the nitty-gritty steps, which have been in between the maps of intensity to the calibrated maps, the quantified maps we want to get from our map we have been acquiring on the garnet and the plagioclase. One thing and one prerequisite I did in between is I used the default tools from XMapTools to generate masked files. So I'm using the intensity map you see here, now again vanadium, is to identify the garnet and mask only the pixels which are belonging to a garnet or plagioclase or amphibole, to now being able to only use those specific masked intensity maps and send them to the calibration module to then individually calibrate those different mineral phases one by one. So for doing this calibration, what I'm doing is I'm going here in the top menu to calibrate. And the first step is we need the primary standards we have been saving earlier in the converter module, and we say import. What it does, it opens you again the window we know from earlier. We go to the folder maps.cps, and in there will be a mat file for the standards we have been saving earlier. We say okay, we open this file, and what it does, it's uploading, and in the down left here in the corner, you see that the standards maps have been updated. And now we see all the 4 primary standards we have been saving earlier. So for example, the GSD1G polynomial, we can investigate now the intensity map, and we see this trend of the polynomial we know from earlier. What it also saves, it saves you the background information of the sample. It also saves you the composition of this reference material, which is the published value in this case. It also gives you information on the sweeps which have been acquired and the pixels. But this is not what we want to do now. We only want to use this information from the primary standard, and we want to come back to our masked mineral phase map. And we want to calibrate now the different phases of plagioclase, garnet, and amphibole. So for doing so, there's a second menu if you're selecting your masked file to calibrate. It opens you the window of the calibration assistant. And this is how it looks like. In the top part here, you see the class, so the mineral phase and the internal standard you want to use, and you are able to select which you want to use for your calibration and internal standardization. In the bottom left, you see the element that is visualized, which you are choosing for the internal standard, or you can either select any other element from the list in the drop-down menu here. And then on the right-hand side, it shows you which primary standard you will be using on an element you're calibrating. So let me give you an example for plagioclase. So we select the plagioclase in the drop-down menu, and I want to calibrate the plagioclase with a more or less homogeneously distributed element as internal standard. In this case, I'm taking silicon, which is robust enough to calibrate, but I need a value to give in the oxide, for example, for the silicon oxide, to use this as a known value, being able to perform the calibration. This value, in this case, could be from any other measurement. In my case, it is from an EPMA measurement, and I know that the rough composition in silicon, it is 57.6 weight%. So I'm entering this number, I'm clicking, and the calibration module is updating the figure and is now able to perform the calibration on the mineral phase of plagioclase, which you can see here. The K matrix is the calibration matrix, and on the right-hand side, you see the now quantified silicon content in plagioclase in micrograms per gram. Now, the big advantage from the module is, and I mentioned that earlier, it is that you're able to now individually for each element we have been measuring, and we measured here 38 from major elements to trace elements, you can select any safe primary standard from earlier to use it as the primary standard for calibration. So in the drop-down menu, you now see all the 4 primary standards. And for example, I want to use the polynomial function, and I can apply to all to change the calibration by GSD with its polynomial function on lithium to lead. But in certain cases, you maybe have a reference material that is performing better on the specific type of mineral phase you want to investigate. For example, the trace elements could be measured and calibrated better with a matrix matching reference material. In this case, and I give you an example here, I could select lanthanum to hafnium, and I want to calibrate this with the NIST 612 class instead of the GSD. So I'm selecting this, and I can apply this setting to the element list, and now the calibration will perform major elements, for example, on the GSD1G, and this range of trace elements with the NIST 612 class as primary standard. If I'm satisfied with my selection, we simply say apply standardization, and we come back to the main menu of XMapTools. And what you can find here in the left-hand side, we'll find now the updated quantified element maps. In this case, for example, lithium in plagioclase from the quantification module, now being updated in the main window of XMapTools. Pierre also mentioned the filter for the limit of detection. So hidden after this quantification in the lower left part, you can also find an updated tree for the limit of detection. And if we look closely in detail, we find the plagioclase now and a map of limit of detection per pixel of lithium in plagioclase. And if we investigate this drop-down even more, we also have the information of our sensitivity matrix, which have been used for the calibration, the background, but we're interested in, of course, in the limit of detection. And a simple filter of the limit of detection, you can use by clicking on Plagioclase in the upper menu here. And with the new occurring button, duplicate and apply the limit of detection filter, you will now generate a duplicate of this quantified Plagioclase map in a separate drop-down menu here. And now all the values which are below detection limit will be filtered from the map. And you can see we can find all the maps. So this was the easy step for a mineral phase where we have a homogeneous distributed internal standard as an element. The case for garnet, and I come here now to the garnet and its map of the calcium, is most of the time calcium is being used as the best internal standard, or the better performing internal standard for the quantification procedure and internal standardization. But the problem here is calcium is inhomogeneous in our garnet sample and in most of the samples. So what do we do here? We need a variable composition of calcium in the garnet to perform the quantification. So we come back to the calibration module as we did earlier. We select in the upper part the garnet and the map of calcium, which you can see it is slightly inhomogeneous in this visualization. But we're selecting now the variable composition button down here, which opens you a new window. In this window, you now have to insert values of the intensity map and the value of a measurement, for example, again from EPMA on the same area to match the intensity and a given composition. I would now zoom in two different areas which show a contrast. With my EPMA measurement, I know that with our ROI tool, and I'm circling now here, this part, the mean value of this area was 8.8 weight% of calcium oxide. We enter this value and we can click simply 1 and 2 in this table, and the calibration module automatically knows which values to process into the table. We do this step for the grain down here, and I know from microprobe that it was calcium oxide content of 6.3. I double click and it updates the figure, and now we are able to perform the quantification with a variable composition of the internal standard. If you're now checking the table, we see that the settings we have before, so the calibration of NISTX 12 with the polynomial function for the trace elements from lanthanum to hafnium, have been saved. And we know that this information is good enough, and we can now apply the standardization process and finish the standardization process on our garnet sample, which was inhomogeneous. If we do so, we come back to the main window and we see that garnet is now calibrated and standardized. So for example, we can come back to the vanadium, which we saw earlier, and we see now a beautiful map of your calibrated garnet. I repeat this process briefly for the amphibole because we need it later. So to repeat that for you, if you're clicking this calibration module, you can choose a mineral phase, amphibole. We want to use silicon as a constant value. In this case, we are using 41.6 from microprobe data, and we apply the standardization. And we're ready to go. We have now the three different mineral phases calibrated, and now it's time to visualize them side by side. So a nice tool in the software is that you can go here to image and say a multi-selection. And this here gives you the ability to now select several maps, for example, the vanadium of plagioclase, the vanadium of garnet, and the vanadium in amphibole, which are all been quantified. And you can plot them on a shared scale. And now you see that we have a similar map as Pierre has earlier been showing in his presentation. You can also adapt the log scale from 0.1, for example, to much higher number. And we have now on a log scale the whole map, including amphibole, garnet, and plagioclase. And with this, the presentation for the quantification module is done. We have all mineral phases calibrated, and it goes back to you, Pierre.
Thank you, Thorsten. I'm sure we'll continue in a few minutes, and you are still working in the background on that. So yes, that was the calibration module. And to really shortly summarize what you have seen is that we have improved this multi-phase and multi-standard calibration, and it's very handy because you can easily go phase by phase and check that your settings are the right one for this phase. And you can also select different standards for each element. The variable composition calibration is very important because it allows you to increase the accuracy. In the case of garnet, it's better to calibrate garnet with calcium rather than using silicon that has a high background that has some interferences in the measurements. And also, Thorsten showed you that you have this production of calibrated maps that can be filtered for the limit of detection. So we are nearly done, but the last part that we want to tell you is that if you have your data in XMapTools, you can also use all the other tools that are available in the software. And for laser ICP-MS applications, you would be interested to use, for example, the data conversion that allows you to convert in one click from element microgram per gram to oxide weight % or element weight %, back and forth. You can also use the structural formulas, external functions, and thermobarometry functions that are available in XMapTools. There is this data visualization module where you can plot your data in histograms, binary diagrams, or ternary diagrams, and then you can select ranges of compositions to display where the corresponding pixels are located in your map. And there is also this spider diagram module where you can directly interrogate your maps, but once it has been calibrated. And just to finish on this project, calling again Thorsten, please, Thorsten, show us a few other tools.
Thank you very much, Pierre. I was just finishing with my work. So we are back to the combined map of vanadium, of garnet, amphibole, and plagioclase. What we need now to do is, I want to show you first how can we use the major element data, for example, on the garnet, to express it as the structural meteor formula, this garnet formula, for example, for spessartine. And then in the second step, I want to briefly introduce you to the spider module Pierre has been mentioning. So step one is this, for the structural formula, we have to go to our quantified data. So if you're going here to our garnet, you can right click on this quantified maps, and we can say convert. And this is opening you a little window, this conversion window. In a drop down, you have the full selection of conversion possibilities. So you can use your mass fraction data in microgram per gram to now convert it to the oxides in weight %. And this is what you want to do for being able to perform the structural formula calculations. So I'm saying apply. Now you have a garnet, which is quantified for its oxides in weight %. And we can use this information to now go in the tab of the functions. And here you can find the structural formula calculator. In the drop-down menu here, you have a selection of predefined structural formulas. And we want, in this case, to use the garnet. If you want, you could now even modify the numbers of oxygen or numbers of cations, but I don't want to use that. Sometimes there are different ways for the calculation of the structural formula, for example, by including Fe3+, but we don't want to do this in this case. I want to use basis of 12 oxygen and apply it to my garnet calculation. And what it does, in the background, it will update the resource folder in XMapTools. And what you can find here in the dropdown of the garnet, you now have the full quantified mass mole fraction of spessartine in garnet, which you then can select and visualize and combine it with any other map as I showed you before. This was step one. And this you can do for the predefined mineral phases. Step two is now the spider module. And this is very important because we are measuring trace elements and we want to interpret them. So what we do, we select again the garnet we have been measuring. And we can use this garnet and the module section in the top here to say spider module. It will open you, of course, a new window. And what we see is the overlay of the spider module. On the right-hand side, you see the trace elements which have been selected from the drop-down menu here. So there are certain presets, for example, the REF element chondrite after Taylor and McLennan 85, but you can also normalize your data you give as input against Stun and McDonough database. I'm using here now the REF elements normalized to chondrite composition. And what we can now do, and this is by using this map down here, the quantified map, we're selecting yttrium as a REF element. And with the circle tool, we are now able to extract, similar to a single spot analysis, data from our map. So we know exactly by using the quantified maps where we want to place this interrogation of a single spot, and we can extract now the values for the REF element pattern normalized against Taylor and McLennan 85. We can interrogate several areas in the meantime. If you say hold on, you can take the same circle tool and you go to another area. It adds it to your plot. You can choose a third area you want to compare. You can even choose a fourth area, as many as you want, or you define different shapes of our eyes, or even do a path. For visualization, we also have different color schemes implemented. And this is how you can then visualize extracted data from your map in a spider diagram tool. And it even gives you some uncertainties, for example, on the standard error. In this case, visualized by the dashed lines here. This is all for the spider module, and it goes back to you, Pierre.
Thank you very much, Thorsten. I will follow with you through the demonstration on how efficient it was to start with the raw data that we started at the beginning of the presentation and going through the whole process of generating the maps, calibrating the maps, and ending up with figures that could be nearly inserted in a paper. So we are not finished yet, and I want to introduce you Mona Lueder from the University of Bern, who will show us a few more examples of what you can do with LA-ICP-MS maps in XMapTools. Please, Mona, the stage is yours.
Thank you, Pierre. I want to show you some examples of what you can do with different functions and data visualization on a different project. Here I have an example of a map on rutile with some inclusions, but we're interested in the rutile part. I've done the same steps that Thorsten showed you. I have the intensity maps quantified, filtered for the LOD, and converted to weight % of oxides. And here you can see the zirconium oxide map for rutile. And in the function of XMapTools, we have the possibility to calculate certain thermobarometry calculations. For example, we can calculate zirconium and rutile temperatures. For this, we go into the function section, and here we have to select the mineral that we're interested in this case, rutile. And we want to calculate temperatures for rutile. So we can apply, and this will open a new input window where we have to input the pressure for the sample. It was 10 kilobars, and the silicon activity for the calculations. And it will automatically, here in the result section, give us the calculation of zirconium and rutile temperature for different published calibrations. For example, the ZAC, the original thermometer, the Ferry and Watson thermometer using the activity, the Tompkins et al., and the newest one from Cohen 2020. Another thing I would like to show you with this example is further possibilities for data visualization. For this, we have under the modules part Wait, let me just go back to the trace element data in microgram per gram. So under the modules, we have the data visualization, which will again open another window, and it automatically generates a binary diagram. Let me just choose some trace elements where you can actually see something plotted, and it will automatically generate a binary diagram of your trace element correlation pixel by pixel. You can, so in the first instance, it shows only about 20% of your total map data, but here you can deselect the low resource mode to plot all your data. I won't do that in this case because the computation takes a bit longer, but it is possible. Another interesting thing that you can do here is under the Explore tab, you can select a region of interest. Let me just quickly do that here. So for example, I might be interested in this area of data, and this will show me a map with all the red pixels here being in the area that I selected here. So this is an interesting way where I can look at where in my map is the data that is most interesting to me actually distributed. We have other possibilities in this data visualization module, and one of them are RGB maps. In this case, 3 elements are selected. I will again just select 3 where you can see a bit nicer what's going on. And this is showing you your entire mapping area and with color values which element is distributed. For example, those green areas here you can see relate to high chromium contents. The more pinkish areas would relate to high niobium and zirconium contents. And it is also possible to export those images directly from XMapTools and use them almost ready for publication. This was the data visualization module. And another interesting thing, we can generate GIFs directly from XMapTools. For this, we go, as Thorsten showed you before, on the multi-selection mode for the images. So you can select the maps that you are interested in and then create a multi-plot image. This will generate a new image here. And we can first see all of the individual maps together, and we can have a look in more detail into the single maps, adjust, for example, the upper and lower limits of the color bar, and then go back to seeing all maps combined, and it saved the settings that we set. Now, if we go on this image with right-click, Save as GIF, it will automatically create the GIF, and it will automatically be saved in your working directory. And this is, for example, a very nice feature for looking at garnet rare earth element compositions. And with that, I give it back to you, Pierre.
Thank you very much, Mona, and also thank you, Renée and Thorsten, for those presentation and to show us what we can do with this XMapTools 4.3. I want to quickly summarize what we have shown you today. So we have shown you that we can use XMapTools 4.3 to do the data reduction of LA-ICP-MS for maps, that we have tried to improve the data compatibility, but there is still work in progress, and in the next version, we will be able to read even more data. You can use the multi-phase calibration with this calibration module for optimal accuracy of each calibration, and you can generate fully quantitative maps. We have improved the calibration by using the multi-standard calibration and having the option to have the variable composition calibration to be able to really address the most extreme situations where you have zoned minerals. We have also shown you that you can calculate and use maps of limit of detections, and you can apply filters to remove all the data that are below the limit of detection. And this avoids misinterpreting data that are actually not real measurements. You can do correlative compositional mapping now by LA-ICP-MS as well. And what is really impressive is that at the end, you can obtain the same type of data for major element by LA-ICP-MS and by electron microprobe. And what you see here on the left is this small image. The upper part of the image was acquired with LA-ICP-MS and the lower part was acquired with electron microprobe. And you can't really distinguish the difference in terms of composition. Everything has been integrated in XMapTools. You can use the tools that are available, the conversion, the structural formula, classification, and so on. And XMapTools is open source. It is free for everyone, and it will always remain free to everyone. And what we like is to have a high degree of transparency to report all the errors we find on the website, and they will remain there. We have also been working, and we are still working on trying to improve the help and the training material. We provided an integrated user guide and some resources website with tutorials and articles on how to do each part. And this will be improved in the future for LA-ICP-MS. And we have produced some video tutorials and provided some test data. And everything we have shown you today, as Thorsten has said, has also been published in a recent publication by Markmann et al. In 2024 in chemical geology. So you can find figures that we used in this presentation and all the science behind this presentation in this paper. So it was a real pleasure for us to show you those new capabilities of XMapTools, and I hope that you appreciated this presentation. I would like also to thank the supporting institutions who have made this work possible and who have made that it's possible to release open source software for free for the community use and for industry. The institutions are the University of Bern, the European Research Council, and the Swiss National Science Foundation.